Perfect. Okay, so welcome from my side as well. As the one mentioned, my name is Michael Schimpf, application engineer here for now 2 years in the COC, Center of Competence here in Munich. And I'm really looking forward now presenting you the process expert, because this is a part of my application as well. I'm taking care about process expert in general. My background is I'm working in this business for now like 8 years something, and I worked for several other vendors like Printer, AOI, SPI, and so on. So I'm quite experienced about that. So let's start with the automatic process optimization. Of course, as most of you maybe know, some don't know, we have all our products included in workflows. So workflow meaning planning, virtual production, process optimization, and so on, where you can find yourself during the production on your side. So of course, Process Expert is part of one of these workflows. This is process optimization, and we have several parts of that as well included in this, and these are 3 of them. And so at first we have a virtual print based on the Gerber data, and this Gerber data is determined to suitable process and printing parameters. So at the end, you will get failures out of the Gerber data, or failure where the print may not the best, and how you can improve that. Second, you have autonomously controlled multi-variable experiments. So we have a fractional experiment where we change parameters of the printer measured by the SPI, and this is to improve the process completely in line, to get a better yield at the end of the line, of course. And last but not least, we have the continuous monitoring, of course, adapting the offset all the time and control the offset and optimize the production process and react on trends, not on failures. That's very important, that's the most important stuff, because normally in a normal SPI or normal closed loop is reacting mainly on failures. We don't want to create failures, we want to act on trends, on sets. So, and last but not least, don't forget the self-healing functionalities I go in detail later on. So first, we have the process expert in line. And there you see the deck printing solution, the ASM process lens, which is the hardware of the process expert. And of course, we are not ending with that. We are deck, and so we can support you with all of the stuff, like we are calling it process support products, which means stencils, supports, consumables, whatever you need, you get it from one hand from the deck side. And this is a part of our process expert, of course, the pre-placement. As you see, this is the first step, process expert pre-placement, where we're working right now. But let's have a sneak into the future a little bit, or the near future, which is the process expert placement, where we want to include the C-place, the placement, to improve the process here as well, to support the operator, to help him a little bit, and to improve maybe about some failures about nozzles, pickup rate, and so on. Next step, the future is as well. Sorry, I have a slow-mo here. The post placement, the ASM process expert post placement, where we're working right now actually with Viscom to have an interface between process expert, process engine, and the AOI, so that you can see later on failures on the AOI, what was happening in the SPI, the printer. Maybe you can adapt some values, some limits, whatever. Okay, but this is the sneak into the future, and we're at the status quo. And the status quo is the pre-placement, where we have the autonomous solder paste printing process, the optimization of this, and where we want to stabilize the print before you start. So this is called design for manufacturing health check. And this is what I told you before about that you're working on the Gerber data before you go to the inline, before the complete NPI phase. We have, of course, less operation intervention as a goal, and we want to increase the yield, and we want to stabilize the complete process in line. So what is process expert placement? In fact, it is the process engine. We have the process lens and the deck printer, and this is the process expert. So we have just the hardware is called process lens. It's an SPI or SPM. And we have the brain, which is the process engine, which takes care about all the stuff in the background. And of course, in that combination with the DEC printer, we have the complete solution. But let's go in detail about the process lens and what is about the hardware. The hardware is a so-called 5D inline system. 5D is very important. It's not just marketing. It's really 5D because we're mixing 3D and 2D inline. So very important, if you have a 3D measurement, you have a lot of peaks, you have a lot of background, whatever, because you have the solder resist, you have the copper, whatever, you have a lot of peaks inside, and you don't know exactly where the paste is ending and where it's starting. So what we do in combination, we look on top, and we can definitely say with a gray value where the paste is ending and starting. So we're mixing these 3D and 2D to get a 5D inline system, to have just the real volume, the stable volume of the real measurement. Next stuff is we are using the Moiré phase shifting. So this is very common in the business, that you have phase shifting with a Moiré. You have a field of view, a defined field of view of the system. And within this field of view, we're making 16 pictures within a very short period of time. And so we have a 3D and 2D pictures in the same for one field of view. We have a on-the-fly PCB warp compensation. This is very important because if you don't have the right focus for the aperture, you will never have the right volume detected. So we're detecting all the time the Z-axis, and we are adapting the Z-axis for having always the right focus on that. We are, of course, shadow free, because as well, if you have shadow from one side or the other side, the volume won't be right. So we have different lightings from a lot of sides, and two actuators from left and side, right and left, sorry. And so we don't have any shadow for that. Very important as well, if you come to the CA and you will see the machine live, you will see a lot of stuff from ASM and C-Place stuff, and C-Place side, like transport, whatever. Very important in this case is the pattern camera X and Y position accuracy, because your axis is bending. If you're starting with 20 degrees, 25 degrees, and you're ending with 50, 60, 70 degrees, the axis is always bending. So this has to be compensated, and so C-Place has a lot of pattern about that. So we're working with that to compensate the focus all the time on the fly. Of course, we are at the moment proven for 0105 capability. Of course, the next step will be 0201 metric. We're working on that with a higher resolution, but at the moment 10105 is proven and it's allowed for the system. Oh, sorry. And of course, high-speed programming and the big SPC package is included in the machine because we want to analyze the data and we want to show the data, and of course we want to have some nice pictures in the end. So this is all included inside the machine. That's the technical part. And if we go one step further now, we have the engine, which is the brain I told you, process engine. And the engine has different phases. Like we're starting with the first phase, I told you, with a virtual print. And this is really before production starts or stencil is made or whatever. It's long before the NPI phase. What we're doing here, I lost my screen, guys. Share. Sorry for the interruption. Now you're back again. Should be all good. Okay, back again. First phase of Process Expert, Process Engine. We're having the DFM, Design for Manufacturing HelathCheck, where we have the optimization of the process design before we start with the real stuff. So to go in a little bit in detail, we have the screen of the process engine of the DFM HelathCheck, where we included the Gerber data from stencil, from the board, sorry. and the stencil later on, then we see red areas, yellow areas, and green areas. Red is definitely not printable, in this case, for instance, for the top clamping, for the squeegee. Yellow areas which is not reliable printable, and green areas which are definitely printable. So we need the input from your side, for instance, like changeover frequency, pass side, throughput, solder paste type, high speed, mid speed, low speed. And what we definitely need as well is the surrounding of your printer. What kind of printhead do you have? What kind of squeegee material, stencil, coating, support, clamp type, paste type, most important, of course, and stencil thickness. So, and because of these values, we can say which area is printable and not printable. And this is very, 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 very important because for the printer, we don't have any IPC rule. Maybe we have 1, 2, 3, 4 rules, general rules like 5-ball rule, 7-ball rules, area ratio, open ratio, but that's it. The rest is all about experience. And what you have here is DEC experience at all. Like we counted 300 years of DEC experience, which from our colleagues that worked with this system. And this is status quo. Of course, it's getting more and more and more. So what you get is a lot of experience here, and of course, including the 4 rules, to take care about the print before you start to print, before the stencil design and all the other stuff. Because very often in smaller companies or mid-speed companies or whatever, you don't have the knowledge on time, or you don't have the knowledge in every site, every time, and so on. So this is what you get, a recommendation as well, and at the end you get as well a recommendation for the printer. How to start with a printer, like print speed, separation speed, pressure, and what you see at last, clean rate. We're starting as well with a very moderate clean rate recommendation, and you can transfer this one directly to the printer and start with these values right now. So this is all before you start with a real print. And if you go inline, we have the next step, which is during prototyping or starting for the production. And there we have, of course, at first step, very important, the X, Y, and Zeta offset correction, because this is the most important before we adapt anything in the future. This must be right. This must be perfectly in shape. And next one is a initial wipe optimization. I will go in detail a little bit. And the third one is a fractional experiment. Fractional experiment means really we are taking care about the printer. We are operating the printer. We're changing values like print pressure, separation speed, and print speed in different variations. So let's go in detail a little bit about, we have here the SPC data about the process length. And what you see here, we have the offset in Y, where you can directly see the print direction, front, reverse, and you have the offset in X as well in combination. So after the first adaptation of the offset, you see the offset is going lower and lower and lower. So this is the goal, what we want to have. We want to have a real close process, and after that we can start with the rest of it. So what you see in transfer, if the process is getting closer and closer and closer with the offset in Y, the volume as well is getting closer to your mean value. Of course, that's very, very easy to understand. If you're not on the landing with your paste directly on the landing, your volume will definitely always will differ. And if you're directly on the landing, you will have a repeatable volume of your paste. So that's what we want to have at first step. Second step is clean rate optimization for initial one, the first one. So in this case, for instance, we're starting with 4 boards, and after 4 boards is in a good shape, the offset is in a good shape, we're starting to print to deterioration, so to the end of whatever. In this case, we're starting here 1, 2, 3, 4 boards, 5 boards, still within the limits, 6 boards, 7, and the 8th board is out of the limits of the area in this case. And so we say the failure was between 7 and 8, so we go back to 6, and we get out of the clean rate about 6, where we started with 4. This is the initial stuff. And for the fractional experiment, what we're doing as well, where we're changing the printer parameters, you see here an example for a standard board from us. You see the volume and the count and the normal Gaussian Normalverteilung, sorry to say that in German. Where we see a standard deviation about 10.8, and we have a range about 50 for something about for the volume. And after the experiment, where we changed some different parameters and we look at the results, we had an improvement about 25% of the standard deviation and 16% about the range. So we get the process very stable and stable and stable. And what's the big benefit about this experiment? If we change a parameter, we're saving that to the program. And later on, if you go next day or day after, you have these change parameters saved to the program, and you're starting with a higher level of a stable process. So this can be improved all the time. Okay, and last but not least, we have the real stuff during production, where we still have all the offset correction on the time or on the fly, where we have still have a wipe adjustment, but not the initial one like a higher step, but only in plus minus 1. And last but not least, we have a self-healing stuff, which means if we have, for instance, a bridge coming twice, one board and next board at the same area, another bridge, there is a high chance that we have some stuff below the stencil. So we do a self-healing cleaning, which doesn't affect the normal cleaning cycle. Good, but not too much theory, a little bit more about the real world. So I show you a video, and in this video you can very easily see what it's all about, because you see now here the process engine viewer, and with the process engine viewer you see the process engine, the deck printer, and the process lens, for instance, as well software version, which program is loaded, and you see all the actions which the system is doing, and you can easily follow during inspection here. As well, you can do all the stuff full automated or half automated, so the line, the engineer, or whatever who's taking care about the complete process, has the full action plan here. So if we start with a live tracker, you see a ball, and a ball means if you look at the legend, we have a clean first, then we have a production board, the square is a board, you have a yellow one, we have a green one, and you see the blue arrow, which means is the print direction. So we have 4 boards here now. After 4 boards we have the first clean. You see the printer direction for each, and you see green one, which means we are inside the values of the engine, which means we are below 30, and we are here below higher than 30 for the yellow one. Later on we go with smaller levels for the offset, like 10 microns. So, but what you see here, the green one, the one direction is in a good shape, the other one direction is not in a good shape, so we will have definitely the first offset correction, which occurs in another ball. I think it's a purple ball. Wait, after the second one. Then we have to apply offset correction. You see the purple ball. And this means the first print direction is applied for the correction. Then we have the second direction. And after these first corrections, we will have definitely 4 boards in a row, which are within the limits of the engine. Very important to repeat is, maybe I didn't mention it before, the limits from the engine are very, very close. Much closer than the limits from the process lens, from the SPI itself. Because whatever we want to change with the engine in the background shouldn't affect the SPI rules, the SPI limits. So everything that we're doing here doesn't say that we're producing bad boards. So all the boards will be within the range of the SPI. So we go further, and after the offset correction, what you see on the right side, see the rear stroke, front stroke, and the actual offsets, quite in a good shape now. And after all this stuff is done, we are doing the initial cleaning adaptation. You see on the right side the history of the cleaning, and we're starting with 4 in this case, like you've seen before, 4 boards print, 4 boards print. And now, after we are with the offset good, we're starting to print to deterioration. Means until we touch the limits about the lens about itself. So that means now we have 1, 2, 3, 4 boards. We have a fifth board, number 6, sorry, then 7, and number 8. Now we have definitely something between here because the history goes from 4 to 6. So we have 8 boards. The failure was something between 7 and 8. So we go one step back to number 6. So this is the initial start. That's what we're doing for the production start. What we're doing after that for the cleaning optimization is that we compare 6 boards with the next 6 boards and with the next 6 boards. So we compare number 1, 1, 2, 2, 3, 3, and so on and so on. And if the standard deviation is still good for this comparison, we go with the cleaning cycle higher or lower. If the process is not stable within the range of the engine, we go lower, and if it's stable, we go higher. So if you have a big batch, the cleaning cycle can end at 20, 15, 10, whatever, depending of course on your board. So what you see here, we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, those two, 6. And then we have the current one, the previous one, and the next one will occur in one better or one burst. So 7 is the next one. This is what you have during the production. Okay. So far so good for that. What comes then is we're starting the experiment. The experiment can be done automatically as well, or half automated, whatever you like. And just to repeat myself all the time, it's not affecting the boards. The boards will be good, which the SPI is detecting. So where the limits are very close, like below 10 micron, where we're touching the process itself. And now we're starting the process here, the experiment. And this is the start of the experiment. You have a lot of data. You can configure it yourself, or you can take care. You can let us take care about the data. And then you're starting that. And for the experiment, it's very important to understand that we need several boards. And 1 second. So what we're having here is 26 boards, what you see in gray. And we need 4 boards at first for the stabilization that we can compare with later on. Then we have 18 boards where we change the parameters, these 3 parameters like print pressure, separation speed, and print speed in different combinations with high, medium, and low level. And at the end we have 4 boards, which are the confirmation boards that we can compare the first 4 boards with the last 4 boards and compare the standard deviation for the volume. So we're starting with that, and within the engine viewer you can see all the time what's the engine is doing, what the printer is doing, which parameter are adapted here, in which kind of setup. And very important to understand as well, we are always cleaning between the 18 boards because the process must be repeatable. Of course, the process won't be good after the print, but it is repeatable after the cleaning. So we are printing, cleaning, printing, and cleaning. And then we go a little bit in the future here and see the end of the experiment. So what we will see is the result of the experiment with the viewer. Let's give me some seconds. Yeah. So we have here the experiment results. We have the pressure. We have the lower level. Instance level 1 means 5. Vector print speed means lower level means 72 millimeters in this case per second. And separation speed means the higher level in this case is 5.5. So these values are taken out the best for the future. So we have an initial standard deviation about 9, and then we ended with these values about a standard deviation about 7.26, which is a high improvement for the process. And we apply that and saved it to the program, and then we are finished with the experiment and we're saving to your program for the next batch. So that's it for the video. We go one step further, and this is the summary. If my presentation is, the summary about it. What do we have for the design of manufacturing health check? The first step is we want to get it right before the implementation in the manufacturing area. So very important is to shorten the NPI phase, because we want to get the process in control. We want to provide a known and stable good starting point from our DEC experience, and we want to use an extensive and unique process knowledge database from our side. So your benefit is about very easy. It's analyzing the stencil layout before you do anything, and you get some process parameters out of that. You have a big cost saving and time saving effect of that, of course. Because normally very often we have customers, they have a new product, then you go with you order a stencil, you're stopping the line maybe, you're doing some test prints, you analyze that, then you see some failures. So you do that, you order the second stencil with some changes, and so on and so on and so on. We have customers who they're doing that like 2 times, 3 times, 4 times, even 5 times, still until they have a stable process. So we will we will dramatically shorten that with DFM health check. So check for the DFM health check. That's right. Second is during prototype or production. So we have the automated optimization on the production line. And what we're doing is to maintain the solder paste printing process centered. So this is the first step, definitely, like I explained before. Before we change anything, we have to focus on the offset, and we have to bring the offset very close to 0. And what is important, again and again, we don't want to act on failures. We act on small drifts, on trends, and we don't want to generate printing defects. Again, we're using our knowledge database for that, and which the database is always as well getting more and more with the experience of your product. So your benefits is easy to understand. It's of course reducing intervention from the operator. Everybody wants to have the operator for other stuff, or wants to have a one operator per line in the future. So this is the base for it. Without don't create failures on the print. Don't annoy the operator. Don't come to the SPI for doing debugging or something. We want to increase the yield. Of course, 100% is our goal. For everybody should be the goal, but this is definitely not realistic, but it's a yield and it's a goal. We want to increase the process stability, and this is most important, of course. And last but not least, during production, I mentioned it before, we have still the offset correction all the time. If you're changing your batch, for instance, if you have a different stretch, we can react on that very easily. We have still the wipe adjustment all the time, which is ongoing, and we have the self-healing function at the end. So you have the stabilization, the automated process optimization, and the proactive control all the time on your system. So that's it for the presentation. Thank you very much for listening.